All right, awesome. So thank you for the introduction. So I'm actually going to be talking about two projects today. All right, I'm not going to touch it. All right, so I'm actually going to be talking about two projects today. And so both of these projects are actually a collaboration between a large number of students. So I actually haven't listed all of them here because it's quite a few of us. So we actually are very fortunate working in AR and VR here at Berkeley. So in addition to the PhD students working on the projects, we also have a AR and VR master's program for which we have students who work with us with their capstone projects. And additionally, we have a VR club that now has over 200 students who are all very passionate undergraduate students who are very capable and also assist in this research. And so this research has all three levels contributing and has allowed us to do a lot more than we would be able to do otherwise. So this first project is, OpenArc is the open source augmented reality solution. And so you might be wondering, well, why am I presenting this at a drone conference? And so there's two reasons. So the first is that the technology used in AR and VR, you will see, is actually very similar in a lot of ways to the technology that's used in drones. And so the technology can kind of be used cross-platform between them, and we actually have plans to do that with putting this technology in a lot of our drones. And so that's relevant already. But also, I personally think that AR and VR is going to be very important for the future of drones and for controlling drones and interacting with drones in the future. And so we'll talk about it a little bit with this project and much more into the second project with how that may work and may play out in the future. So getting into this, in 2016, Goldman Sachs believed that augmented and virtual reality would grow to be a $182 billion market by the year 2025. So a recent survey asked, well, what's the biggest obstacle for us getting from here to there, to the mass adoption of AR and VR technology? And the answer was user experience. And this is a bit of an interesting point because it hints that we're not waiting for some big advancement or breakthrough in technology. What we really need is more people working together to create better experiences. So OpenArc, when we started it, was kind of with a relatively simple idea. So what if we took one aspect of user experience, specifically high accuracy, fast hand tracking, and then we release it as open source. And this would kind of be a first step to pushing the industry forward by allowing more players to create better experiences. Since then, OpenArc has developed into an entire open ecosystem that seeks to push the industry forward. So Berkeley has kind of a long history of developing high-impact open source projects. So from BSD Linux to Apache Spark, or now Caffe for deep learning. OpenArc, we believe, can have that same kind of impact. And we believe that OpenArc can do for AR and VR what Linux did for PC or Android did for mobile. OpenArc provides all the necessary functionality to develop a state-of-the-art augmented reality solution. In fact, OpenArc is the only open source solution that provides all the necessary functionality for state-of-the-art augmented reality. We're at a stage now in the technology where you can easily buy consumer depth cameras that enable this functionality. And so we support a wide variety of these different depth cameras, from Intel RealSense to PMD to Kinect, and now even some fully integrated devices such as the HTC Vive Focus. And these depth cameras are continuing to come out more and more every day, and we continue to expand the list that we include. So I'm just going to go ahead and show some videos that demonstrate the main applications or the main functions of OpenArc.
OpenArc is the open source augmented reality. The software is designed to power a multitude of core functionalities and a wide range of off-the-shelf functions. Currently, OpenArc supports the PMD Pico depth camera and the Intel SR300. These depth sensors could be attached to a variety of hardware such as tablets, helmets, or see-through AR glasses. For today, I'm going to use a helmet setup to free both of my hands. OpenArc is able to accurately determine the location of fingertips in all postures. We're able to do this in real time with no additional sensors on the hand. The algorithm is 98.6% accurate of the standard CVAR hand dataset. The tracking can be done under heavy background interference. Under these conditions, both hands can be tracked independently while maintaining accuracy and performance. We designed OpenArc to support multi-user collaboration that is able to differentiate between your hand and someone else's hand. We also support tactile feedback in AR. Here we track your hands even when it is physically contacting another surface. We created 3 demos to show how you can use OpenArc to create fluid interactions in augmented reality. Here I place some blocks on a surface that is physically clicking the surface. I can tilt the book to make the blocks fall off as it would in the real world. We can localize with any arbitrary surface that has features to bring one on. This time I'm going to place some blocks and move them with a pinch gesture. Finally, I'm going to knock them down with my finger. In this demo, I created 2-handed gestures with OpenArc. I can select an object of interest with the 2-finger tap. This brings up the controls that allows me to freely rotate and rescale my object. I can use a 5-finger gesture to rotate my row. And I can use a 10-finger gesture to zoom in on my playing field.
Okay, so that's some of the kind of the first feature that we released for OpenArc was this hand tracking. We have since kind of expanded onto some more features. So the next one I'm going to talk about is simultaneous localization and mapping. And so what we've done is allowed you to integrate actually a variety of SLAM systems into OpenArc. And this is our recommended solution that we're showing here, which is a high-end open source solution that we've then modified to add loop closure and relocalization. And so with this solution, we can actually track the user across entire buildings, across multiple floors, and even among disturbances such as fast rotations or people walking through the scene. So you'll actually recognize this is the outdoor area just outside this room, and we can go down the floor, back up, and we can still track very, very accurately where the user is going. And so this is very similar to the type of visual odometry system that you would use on modern-day drones. And one of the things that is kind of like a key enabler to this is that you can now buy commercial cameras very cheaply that are both global shutter, which means it takes the entire image frame at once rather than row by row, which is most of your cell phone cameras do. And also time-synchronized IMUs, which just means that the IMU is using the exact same clock that the camera is, which is typically hard to do unless they're already in an integrated package. So on top of the SLAM system, what we've included is volumetric 3D reconstruction. So this allows us to create a 3D model of the entire scene and do so in real time. What we do is first we actually create a very high resolution mesh of the model that is then textured, and then we can automatically subsample that mesh to be a small size model that you could easily share with others or put onto a different PC. And so we can actually downscale to 1/10 of the file size while still keeping all of the structure of the scene. And so this is just one of the models that we can create. And so we can also then segment the model out and segment out individual objects from the model, which is useful for things like if you want to scan objects in the room and then 3D print them or track them or a variety of other tasks. So one of the things that we're also very happy about that we've done for this is we've included Unity support. And this is important. So Unity CEO was recently quoted by saying over 60 to 70% of everything built for augmented and virtual reality was built in Unity. So Unity is traditionally thought of as a game development platform, but it's actually expanded now since the advent of augmented virtual reality. And this is really 60 to 70% of absolutely everything, so not just games, is built in Unity for AR and VR. And so by adding this support to OpenArc, we make it very easy for developers to port their products to OpenArc or use the skills that they've learned over the years to develop new products for OpenArc. So we would like to talk briefly about, we have a lot of partners with OpenArc, and so one of them is a company that's out of Berkeley here that is using OpenArc. So they're a new Berkeley startup, and what they're doing is using augmented and virtual reality to link experts to users in the field in order to provide complex advice. This is primarily as an industry solution. And so we're really excited to say that they've recently, with this product, won the Mixed Reality Award at the Microsoft Imagine Cup World Finals, which is a very prestigious award. And so just kind of to illustrate one of the connections to drones here, I'm going to show one of their public videos.
Pengram is a next-generation assistant solution that allows 3D instructions to be overlaid in augmented reality. With Pengram, the expert can give precise localized instructions, removing ambiguities in traditional video calls or instruction manuals. Here, the remote expert in the blue floating avatar demonstrates how to fix a drone in an off-site VR device, and Pengram translates his or her movements to an on-site operator in AR. It is as if both individuals are working in the same space. The expert can either give instructions in real time or record his or her movements with Pengram's recording tool, which means instructions can be played back multiple times offline. Within Pengram's environment, the expert has access to a rich set of tools that allow the creation of precise annotations and intuitive visual cues. The goal of Pengram is to eliminate ambiguities that comes with complex operations.
Yeah, so that's just a brief kind of video of one of the reasons that augmented and virtual reality might be useful in drones and other applications. So now I'm going to go into our second project, which is much more directly drone related and is using augmented and virtual reality for drones. So this is ISACS, which stands for the Immersive Semi-Autonomous Aerial Command System. And ISACS is all about exploring the different ways that we could use augmented and virtual reality to improve the way that we interact and control drones. So the first kind of project that we've decided to tackle is this idea of multiple drone control. So it's been a dream for kind of a long while that, as robots become more and more advanced and we get more automation, we should be able to have a single user controlling multiple robots. And while this has been proposed for a long time, it hasn't really happened yet. And we believe that this is because of a disconnect in information flow between the user and the robot. And we believe that augmented and virtual reality can really help us solve this problem. And so we've taken a kind of three-phase approach to this, dividing it into control, user interface, and human-robot interaction research. So we're very fortunate. We get to use the control system developed by Claire Tomlin's lab, which is fantastic in that it allows us to control the drone's safety, but also provides us safely, but also provides us with all the information of the drone, including exact error bounds for where the drone might be flying. And so I'm not going to talk about too much on the control side since Claire has kind of already talked about that. And so I'll go right into our user interface. So this is our interface that is developed for the solution. So this is an early version where you're able to set waypoints for the drone to fly, and you can easily set up a 3D path for the drone to fly in just a matter of seconds. And so you can see Jesse here is our lead developer, and he's able to easily rotate and scale the system so that you can get full perspective of what's going on in 3D very easily. And so this allows a really non-experienced user to fly the drone in very precise paths, including going through these hoops here in just a matter of seconds. And it's really easy to learn, and we're actually working on the full research to show how easy it is to learn. All right. So the second facet of this project, or the third facet, I guess, is human-robot interaction research. And so this slide looks very, very technical, but it's actually a very simple concept. And so all that we're saying here is that if we have a supervisor who is observing a robot and is trying to help the robot, the supervisor is going to have some idea of how the robot is able to act. And the problem is that this may not be exactly how the robot is able to act, how the robot thinks it's able to act. And so this is another example of that kind of information disconnect. And so a great example to illustrate this is if you've ever driven in a adaptive cruise control vehicle, so specifically the ones that are able to brake as you approach another car. There's this period of time as you're approaching the next car where you're waiting, you're thinking, hey, why is my car not braking? It should be braking. Why are you not braking? And then it starts to brake. And this happens, I mean, if you've ever driven, it's all the time. And this is because the human has a different idea of when the car should be braking in order to be safe than the car does. And so even though the car may know more accurately what this is, it really adds a lot of stress to the user. And so what we've done here is allow the robot to actually learn the user's model for what is a safe action. So the example here is shown here. And so this K here is a object, or the black region is an obstacle that we want to avoid. The green is all those regions that are safe. And then the red here is those regions that if we enter them, we cannot guarantee that the robot will behave safely. And so this region is actually computed using the backwards reachable sets that Claire mentioned earlier. But really all you have to know is that the human's version of what this unsafe set is may not be exactly the same as what the drone's version of what it is. And so whenever the drone or other robot is inside this region, it makes the human uncomfortable, even though the drone may be safe. And so if you were watching this and you were trying to tell, like, I want to find all the situations and make sure the drone doesn't do anything unsafe, you're going to be trying to monitor it, and you're going to mark this as, oh, hey, the drone was unsafe, even though the drone was safe. And so what we've done is actually modify the drone's behavior to learn what the human thinks. And actually, this is really nice because all we actually have to learn with this model is a single parameter, which is this mu here. And so because we're only learning one parameter, we can do this with a very, very small number of samples. We're talking like 10 to 30 samples, which would be equivalent of like, oh, I took my car out and was braking 30 times. So one trip with my car, I'd be able to learn what the correct distance to brake at is. And so with this, we're able to show tests that we can directly predict a false positive reduction in users' behavior by modifying the drone's behavior. And so the learned and conservative models here were two different behaviors that we had the robot act on. And we were almost able to almost directly predict what the false positive reduction is. So this was the predicted reduction, and this was the actual reduction in false positives in our test. So this was really impressive, and we're really excited about this because it gives us a way that we can actually then modify our drone behavior to make it easier for a supervisor to interact with the model. And so we have one last project that I'm going to talk briefly about, which is, we call it Project Iron Man, and I'll show video in just a sec to illustrate. So this project is done by several master's students, and actually I'll go ahead and show the video. So we don't actually have video of the current version of the project, but hopefully this will kind of illustrate where we're at.
Oh, I'm not here. Thank God this business Wi-Fi is moving closely.
So this is kind of where the inspiration of our project came from, was this idea that I want to be able to control a drone remotely as if I was actually in the drone. And so that's where the name of the project came from. But this is a little bit different. So you might think of it kind of like current FPV headsets. So FPV is first-person view. It's a way of controlling drones where you're looking through a camera and you're just wearing what's almost like a virtual reality headset. The problem with this is you only get a single camera and you're restricted to the view that that camera can see. So we believe with the advent of 5G technology and the advancements in 360-degree camera processing, we're actually able to take that and add some computer vision and state estimation in order to provide a real-time, stable view of what the drone is seeing in full 360 at all times. And so this really combines nicely with the rest of the i6 project. And so if you were doing a task such as search and rescue, where you've sent out multiple drones and you've been supervising all of these drones, and then a drone says, hey, I think I found something, you would now be able to zoom in and take control of that drone as if you were in the cockpit of a plane and look all around and see what's going on and really assess the situation in a way that the drone may not be able to as of yet. And so this kind of setup is how we've been tackling this project of we really want to develop a state-of-the-art solution that takes into account user interface, really proves that what we're doing makes sense through human-robot interaction research, and it really develops a safe control system all around it. And so that's, I think, all I have to talk about today. So thank you.